Hi all, welcome to the second part of the lecture on mass transfer. In the first part, we studied different modes of mass transfer, various ways of representing concentration of a species and Fick's law of diffusivity. As is discussed in the first part, diffusion mass transfer is analogous to conduction heat transfer. It is convenient to derive general mass diffusion equations for common geometries, that is Cartesian coordinates, cylindrical coordinates and spherical coordinates. Let's discuss the Cartesian coordinate first. This derivation proceeds as the same way we have done in case of conduction heat transfer. There we apply energy balance equation in the control volume, but here we will apply the mass balance equation. Consider a homogeneous stationary medium consisting of binary mixture of components A and B. Let the mass transfer may occur only by diffusion. Consider a differential control volume of size dx, dy, dz as shown in figure. The mass balance equation here is, this is the mass balance equation in the control volume. The total mass accumulated in the control volume due to mass diffusion in all directions, in x direction, y direction and z direction, plus the mass generated within the control volume due to some chemical reactions should be equal to rate of change of mass concentration of species A within the control volume during a specified time. This is the mass balance equation. So first consider the mass accumulation due to diffusion in all three directions. So the mass of species A diffusing through the control volume in the stationary medium B is given by, along x direction, NaX is the mass flux entering to the control volume through the left space, and NaX plus dx is the mass flux leaving the control volume from the right face. So mass influx is equal to NaX into the area across the diffusion, that is dy dz. This is the area across the diffusion process. So here NaX is mass flux, mass flow rate per unit area. The total mass flow rate will be equal to NaX into the cross section area across the mass flow direction. So mass Flux is equal to NaX plus dx dy dz. Dy dz is the same cross section area in x direction. That is equal to NaX dy dz plus dou by dou x of NaX dy dz to the distance dx. dx is the size along x direction. So rate of change of NaX through the distance dx, dou by dou x of NaX dy dz dx. So accumulation of species A in the control volume due to these interactions, due to the diffusion in x direction, equal to mass influx minus mass efflux. The mass entering into the control volume in x direction minus mass leaving the control volume in x direction. That will be equal to minus of dou by dou x NaX dy dz dx. That is the mass accumulation within the control volume due to the diffusion in x direction. Similarly, mass accumulation of species A along y direction and z directions is given by same procedure. We can repeat. In y direction, the mass accumulation is equal to minus dou by dou y NaY dx dy dz, where NaY is the MA mass flow rate per unit area. In z direction, minus dou by dou z of NaZ dx dy dz, where NaZ is the mass flow rate per unit area, mass flux in z direction. Now, the total or net accumulation of mass species A due to the diffusion in all three directions is equal to sum of all above quantities, that is minus of dou by dou x nax plus dou by dou y nay plus dou by dou z naz, the whole multiplied with the volume of the element dx dy dz. This equation is equation number 1. Now we assume volumetric mass generation of species A within the control medium as a result of chemical reactions. MAG is equal to, that is the volumetric mass generation of species A within the control medium. This is equal to NAG dx dy dz, where NAG is the rate of increase of the mass of species A due to chemical reactions per unit volume of it. Its unit is kilogram per meter cube second, or rate per meter, that is NAG. The total mass generation is equal to NAG multiplied with its volume. So this is the mass balance equation. The right hand side, rate of change of mass concentration of species A within the control volume is equal to, let rho A mass concentration of species A in kilogram per meter cube and tau the time duration of the mass flow. Therefore, rate of change of mass concentration is equal to dou rho A by dou T dx dy during the time tau, dou rho A by dou tau in the control volume dx dy dz. According to the mass balance equation, we can equate all these three equations. Equation number 1, mass diffusion along all directions. Second equation is mass generation along chemical reactions, and the rate of change of concentration is the third equation. So by applying mass balance, we will get minus dou by dou x of nax plus dou by dou of nay plus dou by dou z naz dx dy dz, the mass accumulation due to the diffusion in all directions, plus nag dx dy dz, this is the mass generation due to chemical reaction, it is equal to dou rho A by dou tau dx dy dz, the rate of change of mass constant and during time tau. From Fick's law of diffusion, you can cancel all these volume terms dx dy dz, then apply the Fick's law here. The above equation can be written as nax, that is ma by a equal to minus dab dou rho A by dou x, that is the Fick's law of diffusion in one direction. nax is equal to ma by a, mass flux in its direction of species A, that is equal to Fick's law, is equal to minus of dab dou rho A by dou x. Here we have a minus sign at the outside, and inside, if you apply the Fick's law, we have a minus sign. So minus sign will be positive. So plus the second term will be dou by dou of dab dou rho A by dou y plus dou by dou z of dab dou rho A by dou z plus nag equal to dou rho A by dou tau. If the diffusion coefficients of A to B is constant throughout the medium and density of the mixture is also constant, then this equation will be to dou square by dou x square rho A plus dou square by dou y square rho A plus dou square by dou z square rho A plus nag by dab equal to 1 by dab dou rho A by. This equation is the general mass diffusion equation in a Cartesian coordinates. Now, if we reduce this general mass diffusion equation in a Cartesian coordinates to a one-dimensional steady state case, the general mass diffusion equation reduces to d square rho A by dx square. That means there is only one dimension, one direction, so that is x direction. This term, and there is no heat generation to this term, and it is steady state. Because of steady state, this term will be also. So your equation reduces to dou square rho A by dou x square is equal to 0. That is d square rho A by dx square is equal to 0, because it is one dimensional heat conduction. Consider a plane wall. Here left side mass concentration rho A1 and the right side is rho A2. Rho A1 is greater than rho A2, so there will be diffusion mass transfer in this plane. So you will get a concentration profile here, and the thickness of the plane bond is L, is the positive x direction. So your general mass diffusion equation, differential equation for this one-dimensional steady-state plane bond, it reduces to d square rho a by dx horizontal. So to get the mass concentration rho a, integrate twice this equation and apply the boundary conditions. So upon integrate twice, you will get rho a is c1x plus c. This is 1. Now apply the boundary condition. First boundary condition is at x is equal to 0, that is this wall, the density, mass density, mass concentration rho a is equal to rho a1. So your equation changes to rho a is equal to rho a1 equal to c2. At x is equal to L, that is the other boundary condition, that is this phase, this plane. So here mass concentration is rho a2. At x is equal to L, rho a is equal to rho a2. Apply this here, you will get rho a2 equal to c1L plus c2. C2 is already, we have rho a1. So you will get c1 is equal to constant, c1 is constant integration, c1 is equal to rho a2 minus rho a1 divided by L. So put the values of c2 and c1 in equation of 1 with the concentration profile equation here. Okay, rho a is equal to rho a2 minus rho a1 divided by L of x plus rho 1. In dimensionless form, you get rho a minus rho a1 divided by rho a2 minus rho a1. Keep explain. The rho a is the concentration of species A at a distance x from the left face. Okay. Rho a1 is the concentration of species at the left face. Rho a2 is the concentration of species at the right face. The plane one we consider. From this equation, we say that the concentration profile is a straight line. To find the mass transfer rate, apply the Fick's law equation. According to Fick's law, ma by a is equal to minus dab d rho a by dx. That is equal to d rho a by dx. You will get rho a2 minus rho a1 by L. Rho a2 minus rho a1 by L is d rho a by dx. Get c1x. So c1 value is rho a2 minus rho a1 by L. So d rho a by dx will be ma by a is equal to minus dab rho a2 minus rho a1 by L. That's equal to, in terms of resistance concepts, you can rewrite this equation as ma equal to this a, you can write here the denominator on the right side. So you will get rho a1 minus rho a2 L by a dab, capital A dab. The denominator term L by a dab is called diffusion resistance. Right? Like what? Diffusion resistance. Okay. This is exactly analogous to the conduction heat transfer through a plane bond. Now the rate of mass diffusion through a plane bond is proportional to the average density, wall area, and concentration difference across the bond, but it is inversely proportional to the wall thickness. So the above equation we can represent other terms on mass basis. We can represent it with the mass fraction, in terms of mass fraction, we can represent it m equal to mass diffusion of species A to the wall, through the wall, is equal to rho VABA WA1 minus WA2 by L, where WA1 is the mass fraction at the left side, WA2 is the mass fraction at the right side. What? That is equal to BABA rho A1 minus rho A2 by L, if rho is constant. Okay. So we can rewrite this equation as OA1 minus OA2 will be L by 2 ABA. That is the denominator like this, or diffusion resistance what? Its unit is second per meter. So on mole basis, we can represent it in terms of mole fraction where A. That is mole diffusion, molar diffusion of A to the wall equal to C dA YA1 minus YA2 to PL, where C is the molar concentration, the mixer. That is equal to, if C is constant throughout the mixer, then DABA CA1 minus CA2 L. Right? CA1 minus CA2 by L by into A. L by CPA. A. If we represent it with the mole fraction, this will be the molar resistance. If you represent it with the molar concentration Ca minus C2, the molar diffusion resistance will be L by ADA. So we extend these derivations in case of cylindrical and spherical shell. The same procedure you can follow to find the general mass diffusion equation to cylindrical and spherical shell. You do it yourself. Finally, if we reduce that general mass diffusion equation into a steady state one-dimensional diffusion to a hollow cylindrical shell of inside radius R1 and outside radius R2, and mass fraction at the inside wall is WA1, mass fraction of species A outside of the wall is WA2, and the diffusion of species A through the cylindrical wall of species B will be equal to MA equal to rho A1 minus rho A2 divided by ln of R2 by R1 by L. All the derivations are similar to convection transfer. Similar way you can derive one-dimensional mass transfer equation, mass diffusion equation to cylindrical coordinates as well. So mass flow rate M of species A to the membrane equal to rho A1 minus rho A2 ln of R2 by R1 by L. And this denominator term, all this denominator term is called the diffusion resistance of the cylindrical shell. This equation you can, where L is the length of the cylinder, and this equation you can find from the data for weight. R1 and R2 are outside the cylinder. Same way, this same figure we can use for spherical shell also. You will get the equation MA is equal to the mass of species A, diffusion of species A through mass diffusion of species A to the spherical shell of species B equal to rho A1 minus rho A2 R2 minus R1 or by DAB R1 R2. So the denominator term will be the diffusion resistance of spherical shell. R2 minus R1 by R1. In data book page number 184, equation number 8, you can find this equation, but DAB, the term DAB is missing the equation. So please keep it in mind. Again, these equations in case of cylindrical and spherical shell also we can represent in terms of mass fraction and mole fraction. Okay, that is this one. Mole basis it will be mole fraction, and on mass basis it will be mass fraction. Okay, if mass fraction is there, then 2 pi L dAb rho will be there. If it is mole fraction, then C will be there. Also, the mass diffusion equations we can represent in terms of partial pressure. We consider a solid particle of specific speed, and we are maintaining a gas on both sides of the wall at different pressures. PA1, the cross-section area of the wall is A, and the thickness of the wall is L. Then molar diffusion of species A through the wall because of the pressure difference on either side equal to DAB SA A PA1 PA2 L PA1 and PA2 are the partial pressures of gas on either side of the wall. DAB is a diffusion coefficient of species A, gas A, to the species B wall, and A is the cross-section area of the wall, and SAB is a new term, is called solubility. Its unit is in kilomole per meter cube bar if the pressure times is bar. So where SAB is the solubility of the gas A in the solid. Solubility of gas A, the solid. The molar concentration C can be expressed in terms of solubility and total pressure using this equation. C is equal to solubility SAB E. The product of solubility and the diffusion coefficient DAB SAB is called the permeability. Now we will discuss some problems in this topic. First question is, oxygen gas is maintained at pressures 4 bar and 1 bar on the opposite sides of a 0.2 mm thick rubber membrane, and the entire system is at 25 degrees Celsius. Calculate. First one, molar concentration of oxygen at the opposite faces of the membrane. Second one, molar and mass diffusion flux of oxygen to the membrane. So we need to find molar concentration of oxygen at the opposite faces, molar and mass diffusion flux of oxygen to the, it's a rubber membrane. On either side we are maintaining oxygen at 4 bar and 1 bar, and the thickness of the rubber membrane is 1. So to find molar concentration, use this equation, molar concentration C is equal to S into P, where S is the solubility and P is the total pressure. So on the left side we need to find the concentration, molar concentration C, then the solubility of the oxygen with the rubber multiplied with the pressure maintaining the, that is 4 bar, to give you the molar concentration. So in this problem, solubility of oxygen rubber is not given, so you can find it from the data book page number 190. You have a table on page number 190, binary diffusion coefficient at 1 atmosphere. There is a table, then find solubility of the last column. Here oxygen is diffusing to the rubber, right? So the first table, the last row, you can find it, oxygen to rubber, temperature at 25 degrees Celsius. Diffusion coefficient is given as 0.21 into 10 raised to minus 9 meter square per second. And solubility in kilomole per meter cube are given as 3.12 into 10 raised to minus 3. So note it down. S is equal to 3.12 into 10 raised to minus 3 kilogram mole per meter cube bar solubility, and this is the diffusion coefficient. Now at 4 bar, that is the left side, you CA1, that is molar concentration of oxygen at the left side of the rubber band, equal to use this equation solubility multiplied with that pressure bar to get 0.01248 kilogram mole per meter cube. And at the right side, it is maintained at 1 bar. So CA is equal to molar concentration. CA is equal to 3.12 into 3 minus 3 into 1. That is 3 kilogram mole per meter. Now we need to find molar and mass diffusion flux of oxygen. Okay. Find diffusion flux. You need to check your data book page number 184. There they have given a fixed law equation. Equation number 8 for a solid boundary. Okay, it's a solid boundary, diffusion to solid boundary, similar to conduction. Equation number 8, page number 184, equation number 8. MA by A is equal to TAB, rho A1 minus rho A2 equal to PL. This is the equation to find mass diffusion flux. We need to find molar diffusion flux. This will be the equation in case of NA by MA by A, right? NA by A is equal to DAB. In case of OA, we substitute the value of molar concentration CA1. Equation. Okay, so write this equation first. NA by A is equal to DAB CA1 minus A2 L, where L is the 0.2 meter. So 100 meter. So you will get NA by A is molar diffusion flux. Simple. Substitute all the values, all these values we have. So 9.83 minus 9 kilogram per square second. Okay, and this is the equation for mass flux. This equation directly will find the data page number 184, equation 8. Here we need to find rho A1 and rho A2. Rho A1 mass concentration is equal to the molar concentration multiplied with the mass molecular weight of the oxygen. Gets rho A1 molar concentration. Okay. So molecular weight of oxygen. Molecular weight of oxygen you can find from page number 190. Page number 192. There is a table, Schmidt number of gases in dilute mixture with air. That table they have given molecular weight of the species and also the Schmidt number. Okay. So here the species is oxygen, gas is oxygen. So oxygen at the bottom in that table, bottom you will find molecular weight of the oxygen is 32. Okay. So rho A1 is equal to CA1 to MA, that is molecular weight. That's rho A1. Okay, and rho A2 is also CA2 multiplied with the molecular weight of oxygen. Okay, remaining all the terms are same. So we just multiply Na by A, that is the molar diffusion flux, multiplied with the molecular weight of the oxygen, you get the mass flux, mass diffusion flux. So 9.828 10 raised to minus 9 multiplied with molecular weight of oxygen, get the mass diffusion flux. The 3.14496 into 10 raised to minus 7 kilogram per meter square. First question. let's move to the second question. Here we consider a cylindrical bowl. Oxygen at 25 degrees Celsius at a pressure of 2 bar flows through a rubber pipe of inside radius 25 mm while thickness is 2.5 millimeter. The diffusivity of oxygen to rubber 2 is 0.21 into 10 raised to minus 9 meters per second, and the solubility of oxygen rubber is 3.12 3 kilogram mole per bar. So in this problem they have given diffusion coefficient and solubility. It is not there, find it from the data. Find the loss of oxygen by diffusion per meter length of pipe. Mole proportion of oxygen, that is percentage volume of oxygen in air, is equal to 21%. So let's draw a hollow cylindrical pipe first. It's a rubber pipe. It is rubber. B constant B is rubber and oxygen is constant A. Okay. Oxygen is maintained at 2 bar at the inside, given pressure is 2 bar, and at the outside there is 1 bar. If it is not given, assume it is 1 bar. So inside radius is 0.025 meter, thickness is given as 2.5 millimeter. So R2 is equal to inside radius plus thickness, we get 0.0275 meter. So R2 minus R1 is the thickness 0.007. Now DAD is given. We need to find the molar concentration at inside. That is CA1 is equal to solubility multiplied by inside pressure. Solubility is given, inside pressure is given. So you can calculate CA1, that is 6.24 raised to minus 3 kilogram. CA2 is equal to solubility to the outside pressure of oxygen. Outside pressure of oxygen should be equal to 0.21 into lambda, because it is given mole proportion of oxygen in air is equal to 0.6. Okay. So it's outside we have atmospheric air. So inside we have pure oxygen. So the mole proportion of oxygen at the outside atmospheric air is 0.21. So it is maintained at 1 bar, then the outside pressure of oxygen will be that mole proportion multiplied with the total pressure of the air. So that will be 0.21. So CA2 will be equal to solubility multiplied with the outside pressure of oxygen, that is 0.1 bar, that is equal to 6.55 from data book page number 184 equation 8, you can find the equation in MA equal for hollow cylinder of length L, MA equal to 2 pi DAB L rho A1 minus rho A2, rho A1 minus rho A2 by ln of R2 by R1. So if we change it in case of molar flux, MA, we will just change CA1 and CA2 in place of rho A1 and rho A2. Okay, this is equal to molar concentration 2 pi L dAB. In place of rho A1 and rho A2, substitute CA1 and CA2. Ca1 minus Ca2 of R2 by R1. So substitute all these values. For all the values we have Ca1, Ca2, L, Kb, R1, R1, we have to get Na by N, Na by N. Per unit length, we have to find out. So mole per unit length equal to 7.73 raised to minus 7 kilogram per meter second. So we need to find the loss of oxygen per meter length. Find the loss of oxygen by diffusion per meter length. So loss of oxygen in terms of kilogram per second multiplied this mole flux molar diffusion with the molecular weight of gas oxygen. So Na by N multiplied Ma give you the loss of oxygen per kilogram per second. I repeat, 2.47 is to minus 9 kilogram per second. The last problem in this topic is hydrogen gas at 2 bar and 300 Kelvin flows through a rubber tubing of 10 mm inside radius and 20 mm outside radius. Hydrogen, the gas is hydrogen, the tubing is rubber. The diffusivity of hydrogen to rubber is 0.75 square per hour. It is given in hour. And solubility of hydrogen is 0.052 meter cube of hydrogen per meter cube of rubber. Here there is a unique change in the solubility. At 1 atmosphere. Find out the diffusion loss of hydrogen per meter length. This problem I have selected because of this solubility. Sometimes solubility can be given in terms of meter cube per meter cube. Okay, unit will be meter cube per meter cube of rubber. Okay, so it is given that R1, R2 pressure at the inside is 2 bar, pressure at the outside is 1 atmosphere, atmospheric pressure. So the temperature is also given, it's 300 Kelvin at the inside. Okay. The diffusion coefficient also given, it is given in meters square per hour, so convert it to second, get 2.08. Solubility of hydrogen is given as 0.052 meter cube per meter cube of rubber. Okay, in this case, we need to find the concentration of hydrogen at inside and outside. To find the concentration of oxygen at inside and outside, apply the characteristic gas equation. Okay. So before going to apply the characteristic gas equation at the inside, we need to find solubility of hydrogen at the inside of the pipe. Okay. The inside it is 2 bar and the solubility of hydrogen is given at 1 atmosphere. Okay, we need to change that corresponding to the 2 bar. 2 bar. The solubility of hydrogen at the operating pressure of 2 bar is suppose V1 is equal to solubility we denoted here with the letter V1 because it is given against Kb. in the unit meter cube per meter cube of rubber. Okay, meter cube per meter cube. So denote it with the V1. That is equal to 2 into 0.05. Okay, 0.05. So you will get 0.104 meter cube per meter cube of rubber. That is the solubility of rubber. Solubility of hydrogen in rubber inside surface. From characteristic gas equation, we have P1 divided by P1. In this equation, R is equal to the characteristic gas constant. Characteristic gas constant of hydrogen, that will be equal to G by molecular weight of hydrogen. G is the universal gas constant, that value we know 8314 kilomole per kilogram Kelvin. So if we divide it with the molecular weight of hydrogen, that is 2, we will get 4157 joule per kilogram Kelvin. 4157 joule per Kelvin. And if we substitute all these values here, you will get the mass of hydrogen, mass flow rate. Here this is not mass flow rate, it's the density of the hydrogen at the inside. That's the mass concentration inside. Is M1 is equal to M1 is ρA1. ρA1 is equal to 0.01668 kilogram per meter cube of water. If we check for the dimensional homogeneity of both sides, if M1 is in kilogram per meter cube only, that will be true. Okay, so P1 is in Newton per meter square, V1 is meter cube of water, and R is in Newton meter per kilogram Kelvin per kilogram Kelvin, Newton meter per kilogram Kelvin, and P is in Kelvin. So you will get dimensional homogeneity only when this term will be in kilogram per meter cube of water. This is the density or concentration of hydrogen inside. Same way, mass concentration of hydrogen. So this is the mass concentration of hydrogen at the inner surface of the tubing. Similarly, at the outer surface, by assuming the pressure is constant, the solubility of hydrogen at 300 Kelvin is. Okay. V out is equal to V out is equal to 1.01325. That is pressure at outside in bar. Okay. So 1.01 bar is equal to 1 atmosphere multiplied with solubility of hydrogen 0.052. So we get 0.05269. So we need to find out the concentration of hydrogen at the outer surface of the rubber tubing by applying characteristic gas equation. M1T, where M is the flow T2. That is equal to 4.28 into 10 raised to minus 3 kilogram of rubber. Therefore, mass concentration of hydrogen at the outer surface is mass concentration. So, is equal to 4.28 into 10 raised to minus 3 kilogram of rubber. So, we have diffusion rate through a cylindrical system. It's from data book page number 198. MA is equal to 2 pi DL need to find out per meter length. So MA is equal to, let's put all the values. Here OA1 and OA2 are MA1 and MA2. Okay. So MI, substitute that values. So inside and outside radius is there, DAB is there, lead is there, lines MA is equal to 8.42 meter, 6 per hour. So sometimes solubility will be given in terms of meter cube of other constituents. At that time, we need to find concentration by using direct series equation, where PV is equal to MRP equation, where M is in the kilogram per meter. So the next topic we will discuss the next part. Thank you all.